Hello students, welcome to Sulfuric classes. Now we are doing over here today Ley oxidation. It is also known as tetrapropyl ammonium perrunate oxidation reaction. So what is over here? It is basically an organic salt of a perrunate ion, that is the negative part, and with large cations, which are basically tetrapropyl ammonium ion or a tetrabutyl ammonium ion. So this will help this particular inorganic anion to enter into organic solvents, and obviously that can be used now as a milder oxidizing agent. Okay, so it was developed by Ley and co-workers, and it was used for selective oxidation for primary and secondary alcohols without the undesired cleavage of any double bonds, which is a problem with oxidizing agents when we are trying to do this type of reactions in presence of unsaturation. Okay, that is CC double bond. So this again takes place in catalytic amount, and we are using a co-oxidant, which is basically over here the N-methyl morpholine in oxide. Okay, if you remember, this was also used as a co-oxidant in osmium tetroxide. Okay, so the catalytic process is basically to convert primary and secondary alcohols to aldehyde and ketones, and as we had said, that this is the Ley oxidation. Now over here it can be either primary, secondary. Let's look at the reaction conditions. Very small amount is used over here. This is the co-oxidant. We are using 4 angstrom molecular sieves over here. Reaction is taking place at room temperature, and over here R can be H, alkyl, aryl, alkenyl, alkynyl, and the solvent over here basically is an organic solvent, which is CH2Cl2 or MECN, right, which is the acetic nitride basically. So 1 degree goes to aldehyde and 2 degree goes to ketone. Next, this is the mechanism over here. This is the structure of the perrunate, and over here we are using tetrapropyl ammonium ion, and so this particular alcohol, which is a secondary alcohol, coordinates again with the metal, just like in the cases of Jones reagent. So ruthenium form, it is in +7 state. Okay, and here we can see that just like in the chromate ester, this is also a ruthenate ester of the alcohol, and abstraction takes place intermolecularly over here. Hydrogen is being removed from here, use of this oxygen, and then it cleaves away to form the ketone. Ruthenium is in +5 state, would be reacting with, so it's leaving away the water, it forms ruthenium in +5 state. Again, that would react with the co-oxidant to reoxidize itself to form the TPAP. So this is the role of the co-oxidant to regenerate the catalyst. Now, some reactions, as we can see, we have an epoxide. Again, in presence of an epoxide, we are oxidizing a primary alcohol to aldehyde. Okay. Next, as we can see, we have a primary alcohol, and it is being oxidized to aldehyde without affecting the CC double bond over here. As we can see, the action conditions are, see, very low temperature. So it has a good tolerance for functional groups like alkenes, tetrahydropyran ethers, silyl ethers, lactones, or epoxides. Okay. As you can see over here, we have again a epoxide. This is getting converted to C double bond O, and nothing happens to a double bond over here. Okay, so that is what we were trying to highlight. Again, the double bond is not affected. The silyl ether part is not affected. Over here, the ketal is not affected, but the OH group is getting converted to CHO. Again, as in the example, ene not affected. Any type of ester is not affected over here. That is the OAC, or a ether such as OM is not affected. But the primary alcohol is getting converted to the aldehyde group. In the next part, we can see esters are not affected. Epoxide is not affected, but gets converted to aldehyde. Another similar reaction over here, and that leads to aldehyde. Now, one may also use the catalyst over a polymer support, which is called PSP, and it is again a very good oxidant, and the reagent performs better in presence of molecular seeds. Okay, so this is the PSP, which is obviously absorbing the ruthenium salt, and we can have this type of an oxidation to create the aldehyde group. Again, another oxidation of the alcohol, but no generation of N oxides over here. And this is alcohol getting converted to aldehyde. Again, the double bond is not affected, and we can see the OH group is getting converted. Okay, rather now this important part over here that there is using water. So in presence of water with this reagent, it will lead to the formation of an acid. Okay, so this is one thing that I will discuss extensively in the next slides. Now again, the double bond is not affected, neither this one, neither that one. Okay, but this is getting oxidized. Similarly, none of these double bonds are affected. Even the THP O linkage is not affected, but the CH2OH is getting converted to aldehyde. Now, this is the topic that I was trying to discuss. Primary alcohols are over-oxidized to carboxylic acid in presence of this reagent and the co-oxidant. But important part is that there should be some water. So here we have been mentioned oxidation goes to two intermediates. What are these intermediates? Let's have a look. So if you have this alcohol, which is a primary alcohol, and then forms the ester, this is the intermediate one, and this is the intermediate two. So what is happening over here is that because there is a water, it forms a gem diol, and this gem diol is being stabilized. Okay, this gem diol is being that the hydrate of the aldehyde is being stabilized over here, and that being the case, so initially it is getting oxidized to aldehyde, and then aldehyde in presence of water. So if there was no water, further oxidation would have not taken place. Water is there, so this reaction is forming with this intermediate, this aldehyde. Then the water is reacting. There is a Lewis base over here. Okay, Lb means the Lewis base, and now this further oxidation takes place via again this ruthenium acid ester, and then abstraction of the second proton takes place, and we get the acid group. So this is almost very similar to the Jones reagent, okay, where primary alcohols were getting oxidized to uh, alcohols, and once you change the medium from aqueous having some acetone to completely CH to Cl2 using PCC or PDC, there was selective oxidation of the primary alcohol to aldehyde, okay, but no further oxidation. Now, as you can see over here, the same reaction that we saw in the previous slide. Now I have kept it over here. Few more oxidations, again primary alcohol, so it will obviously. Water is there? Yes. So acid. Water is there? Yes. So acid will form. Next, we will do this one in the next slide. Okay.